In this tutorial, we will be discussing crystal solids. In molecular solids, the lattice sites are occupied by molecules such as CO2, water, and sugar. The molecules are held together by intermolecular attractive forces, dispersion forces being the weakest, dipole-dipole attractions, and hydrogen bonds. Because the attractive forces are fairly weak, they tend to have a lower melting point, generally less than 300 degrees Celsius. Water is an example of one of these. It's a liquid at room temperature, which is actually rather surprising considering how light it is. The most molecular substances with similar molar masses are gases at room temperature, such as ammonia or methane. So why is this true? Well, this is all due to the hydrogen bonding. Now remember, when we're referring to hydrogen bonding, we're not referring to true bonds. They're an attraction of the hydrogen bonded to oxygen, nitrogen, or fluorine of one compound being attracted to something else because of the polarity. Water is also an excellent solvent. It dissolves many ionic and polar molecular substances because of its large dipole moment. Now, don't get confused by the terminology. When we're talking about dipole, that means we're talking about a positive and a negative. So the electrons are drifting towards the more electronegative atom. Even many small nonpolar molecules have some solubility in water. It also has a fairly high specific heat for a molecular substance. Finally, it actually expands in water. Water actually expands when it freezes rather than condenses like most other solids. This is making it less dense than its liquid, water, which is why ice floats. So let's talk about that crystal lattice again. When some liquids are allowed to cool slowly, their particles will arrange themselves so as to give the maximum attractive forces, which minimize the solid's overall energy. The result will generally be a crystalline solid. The arrangement of the particles in a crystalline solid is called a crystal lattice. Ionic solids have lattice sites occupied by ions. A lattice site is the corners of a crystal. These are held together by attractions between oppositely charged ions. These are non-directional, meaning that they don't have a specific location it goes to. Every cation attracts all anions around it, and every anion attracts all cations around it. The number of other particles each particle is in contact with is called the coordination number. So if we look at this atom in here, this ion in here, it has 1, 2, 3, 4, 5, 6, 7, 8 ions around it. So therefore the coordination number here would be 8. The higher coordination number, the more interaction and the stronger the attractive forces holding the crystal together. The coordination number depends on its relative size of the cations and anions that maintain the charge balance. Anions are typically larger than cations. Remember, anions gain electrons in the process. Therefore, it's getting bigger. The Z effective is getting smaller, so therefore it's getting bigger. The cations lose electrons in the process. The number of anions that can surround the cation is limited to the size of the cation. The closer the size of the ions are to one another, the higher the coordination number is. So if we take an example of sodium chloride and cesium chloride. Sodium is right here. It has 1, 2, 3, 4, 5, 6 atoms around it. Sodium is far smaller than chlorine. Now look at the size difference between cesium and chlorine. They're much closer in size. So here's our cesium. 1, 2, 3, 4, 5, 6, 7, 8. When the ions are actually closer in size, the coordination number goes up. The smallest unit cell that has the pattern of arrangement for the particles is called the unit cell. Unit cells are three-dimensional, usually containing 2 or 3 layers of particles repeating over and over to give a macroscopic crystal structure to the solid. Starting anywhere in the crystal results in the same unit cell because these are repeating crystals. So what we've done here is notice that there are there's few, I should say, whole atoms here. Instead we have things like an eighth of an atom or a quarter of an atom. That's because when we look at the lattice, it's taking one section that repeats itself. Over here, in order to do that, we have to encompass the cesium, and we're getting all of these atoms or ions involved too. And you could actually stack another cube right on top of it. So that way this atom here would match up with another atom up here, and that eighth of an atom would match up with another eighth of an atom here, and so on and so forth. The packing efficiency is the percentage of volume in the unit cell occupied by particles. The higher the coordination number, the more efficiently the particles are packing together. The lattice point is that each particle in the unit cell is called a lattice point. So each particle in the unit cell is called a lattice point. Lattice planes are planes connecting equivalent points in unit cells throughout the lattice. So if we're looking here, there's 3 basic types of unit cells. This is the first one. It's the simple cubic. There's actually only one atom here. But that's because if we take it, just one corner of it, remember the unit cell slices through the atom. So we only have 1/8 of the atom being shown here in the unit cell. And since we're dealing it with every single corner, 1, 2, 3, 4, 1, 2, 3, 4, there's 8 corners, each of them having 1/8. So 8 times 1/8 is how we got 1 atom per unit cell. This is body-centered cubic. This is like the cesium chloride we saw. We want to make sure that we have the right amount here. So we have the cesium in the middle, and then once again we have 1/8 on every single corner. So we have 8 corners, each with 1/8, plus 1 more in the middle, and that's how we got 2 atoms total. Finally, we have face-centered cubic. This one cuts not only through the corners, but also through the sides. So notice that these are halves here, because the unit cell cuts right through the middle of them. You can kind of see it a little better in this picture up here, where the line goes straight through. And straight through down here, where you have half inside and half outside. So we have one, if you think about a die, if you roll dice, there are 6 sides on a die. So that's how we got 6 there, because there's 6 faces. Each one of those only have 1/2. So 6 times 1/2 is 3. We still have these corners to think about. So since we have 1/8 on each of the corners, and we still have 8 corners, that equals 1. So 1 plus 3 is 4 atoms total in the face-centered cubic cell. So here's a summary of all the unit cells. The simple cubic, which has 1 on each corner. The body-centered cubic, which has 1 in the middle. So body-centered, it's in the center, and 4 and 1/8 on each corner. And then face-centered cubic. So we have 1 on each of the face of the cube. Notice that the coordination number increases as you get more unit cells in there. And therefore, the efficiency also increases. Now, measuring the length in terms of R. When they're referring to R, they're referring to the radius of the atom itself. So this is going to help you solve for determining how many atoms or what the length of each atom in there is. But we will be discussing that in a future tutorial.